perfect. Glad everyone had a chance to tune in again. I'll have a reminder that Python course is happening. Good thing I'm already here. Everyone, hopefully. Again, you can find the OneDrive link on the course website. Oh, and it's telling me my internet connection is unstable. That is great. Just in time for class. And no, I don't have too many tabs open. You have too many tabs open. All right. Cool. Well, let's get started. Just a quick check. Can people hear me?
Tobias,
Okay.
It cuts a little bit.
It cuts a little bit, yeah.
Yeah, it's kind of okay. We can see your screen right now.
Okay.
It cuts a little bit.
Yeah. Well, that's just great. Yeah, this has to do with the Wi-Fi in my building. Yeah. Okay. So what Mark is mentioning is what I just talked about earlier. Can you turn off your video? I feel like it's more personal if we have some video. If it keeps being a real problem, then I'll turn off the video.
Tobias, do you have your VPN active by any chance?
Still cutting out for people? No, my VPN should be.
Okay, just wondering. Okay.
Let's see. Do I have it active? Let's see. I'll stop sharing for a second. No, my VPN is not active.
Okay. I mean, we can hear you perfectly right now.
Cool. Yeah, let's see if there's something else that is.
Looks okay. Yeah.
This is a huge bummer. No, we don't need this. I also have no big shell or anything going on, so should be fine. Maybe I'll. Yeah, no, but these tabs should all be fine. Okay. All right. I will go back and start sharing the screen again. Screen 2. And yeah, maybe for now I'll switch off the video. I just feel like it's nicer to follow if you have a video with it, but I agree if that makes the connection better, we should just go forward. Let's see. Jesus, I shared my chat. Okay. What happened to the video links on the courses webpage? Someone asks in chat. There are still video links here. I think there was some, and they look like they work fine. Yeah, we can watch them just fine. So I don't know what this question is about. So everyone
for a while there was a problem. I think the NYU changed the settings.
Oh yeah. I did see that on the Stack Overflow.
That happened during the weekend. It should be fine right now.
Gotcha. Yeah, right. Anyways, what we were talking about earlier is on the OneDrive link, which you find on the course website, there is the solutions to the assignment from last week, and then there is the new assignment. So after today, you can download those, or after this class, you can download those and cruise through some of those assignments if you want. And Yeah, that's a paper I will for sure read. All right, well, let's get to work. We have a little bit to talk about today. Today is not going to be as intense as last week, Thursday. Today, we mostly want to do some recap. So we know that everyone has kind of firm grasp of the concepts that we've taught so far. And then I've prepared some kind of fun problems that combine a lot of the concepts that we've learned so far. And that actually are maybe somewhat similar to what we would do in our research at points. And we'll get to that when we get to that. So for now, the idea is to do like 5 minutes for each of these next sections. I'm going to read out the questions, and I want you to think about them yourself, answer them yourself, and then I will go over the solutions and the answers to those questions, which shouldn't take too long. And maybe we'll move a little bit more quickly with the first couple of sections. So the first section talks about Conda and what is Conda, why is it useful, what's the command to create a new environment, how do you do that, and how do you activate an environment. And let's give ourselves like 3 minutes for that. And the procedure for updating the Git repository is the same as always, right? Commit your changes if you made any changes, and then Git Fetch, and then change to lecture/6, which is the branch on which we have this lecture. All right, so I'll do a quick timer for that. Zip, 3 minutes. that should be enough for that question. Let's go over that real quick. Gave me some time to practice my meditation skills. What is Conda? Conda is a software for dependency management. Why is it useful? Because oftentimes programs and software that we write needs very specific versions of other programs to work. So if we want to get someone else's code running, we need to know what other software they had in the background other than the code that they actually wrote themselves. And how do you create a new environment? You can create a new environment with zip. Conda create -n new env, and then, you know, package, listing the packages like this. You know, is maybe work version 3. And listing versions like this. Right. There are other ways to create environments, but this is kind of the simplest way. How do you activate an environment? Well, you say conda activate new env, and that should activate the environment. Cool. Next section, you're gonna get, I would say another maybe 4, let's say 4 minutes for this. This is about Git. What is Git? How do you initialize a repository? What does that mean? What are the steps to creating a commit? How are new changes from a remote repository applied? What are branches? And what is the relationship between Git and GitHub? And let's give you 4 minutes for that. Time for meditation. Actually, let's see if we can do that. I'll be back in a bit. How is the signal going for everyone? All right, that should be good. Good, okay. All right, let's go over this real quick. Git, what is Git? Git is a version control system, or VCS. It lets us keep track of code and different versions of code. Also, it is not always super intuitive, and that's an understatement. People that have been using it for a while will still often have to Google stuff. So I know a lot of you folks had issues with Git in the earlier lectures, and even now still. Don't feel bad about that. There's a lot in Git. How do you initialize a repository? Well, you go to your project directory, and then you just type in git init. What does that mean, initializing a repository? Initializing a repository means Git now knows this is a repository, a Git repository, and that means it can keep track of what changes you're making. Just because you've initialized a repository doesn't mean you've actually added any code to your repository. So when you initialize a repository, typically the first thing you'll do, if you've had code in there already, you will try to commit the code you already have. What are the steps to creating a commit? Well, you use git add and then kind of whatever files you want to add. Oftentimes this will just be git add dot. Window of lecture _06 IPython notebook is blank. How can I fix? Wait, are people not able to see my screen share? Oh, okay. Cool. Gotcha. I'll let the TAs handle that. All right, back to how do we create a commit? Well, first we have to add files that we want to keep track of. And then we have to say git commit. And this will usually pop us into our terminal editor in the terminal, or if we say -m, then we can type in the git commit message right here. This is useful for keeping track of, in just a short message, what you've actually done. Important to note, the commit messages have two fields. There's the heading, which should be short and kind of precise, and there's the body of the commit message, into which I usually go on long rants why I'm doing what, because it's useful for me to later look back and see why I made certain changes. How are new changes from a remote repository applied? Well, there's two ways of doing that. We usually use Git Fetch. Git Fetch basically just kind of soft updates your local repository with changes from the remote repository. But it doesn't overwrite, Git Fetch doesn't overwrite files that you've modified from the remote repository, which is why we need you to usually commit your changes before you Git Fetch, because otherwise, if you've touched any important files, they won't be updated. The other way to do it is to use git pull. This will usually only update the current branch that you're on. What is the relationship between Git and GitHub? Git is the software that keeps track of changes. GitHub is a place where you can store repositories. There's a ton of other websites like GitHub, like Bitbucket, buckets, GitLab. GitHub is not the only one. GitHub is what we in Git consider a remote. People kind of conflate these two very often. And again, don't blame yourself for that. Stuff isn't all super trivial. And even experienced folks will have to look up things every once in a while. All right. I promise I'm not going to torture you too much anymore with, there's only 3 more sections like this, and then we get to do the really fun stuff. I've got some fun problems prepared, so I'm really looking forward to that. So I'm just going to give you like 3 minutes for this. And we are going to ask, what are the 4 primitive types in Python? What operators are available for each type? And how do we find the available methods for each type? And 3 minutes from now. All right, that's that. What are the 4 primitive types in Python? Those are integers, floats, booleans, and strings are the primitive types. What operators are available for each type? You can see there's a bunch here available for ints. Ints and floats have the same operators available. We have all the mathematical operators for those. We have regular division, and we have floor division. This is available for all types. This is called the assignment operator, so you can assign it to a variable. Similarly, we can use some of these operators also on strings. The plus for strings means concatenation, and the multiplication means, well, consecutive concatenation. How do we find the available methods for each type? This is a trick question. There's two ways of doing it. We can ask help. This will usually give us a bunch of these, what are called dunder methods, which have a double underscore, which are the ones you don't want to look at, really. And then here come the really interesting methods. Or you can just Google it. Python string methods. Boom. See a bunch of you see a bunch of different websites that want to explain string methods in Python to you. Google is one of the most valuable tools we have as programmers, so just didn't want to undercut that. All right. How do I minimize this? Come on. Zip. Oh well. Next, Boolean expressions. I think I'll give you another 3 minutes for that. Let's take a look. What are the two Boolean values? What would their corresponding representations be for each of the primitive types? And what are the three Boolean operators? And let's start now. We got 3 minutes. Oops. All right. Coming up on 3 minutes. 1 second. Let's get this going. Zip. What are the two Boolean values? Well, those are, oopsie, true and false. what would their corresponding representations be for each of the primitive types? So that would be for a string, the empty string is always false, whereas literally any string that's not an empty string is true. This is often useful when you're checking for input. For floats, I think it should be, for floats 0.0 should be false, and then any other float should be true. Wondering if negative floats, yeah, negative floats are also true. Integers, again, 0 is false, and any other integer is true. And that covers the other primitive types. What are the 3 Boolean operators? Those are and, or, and not. And this is invalid syntax. And or not. Yep. But yeah, those are the 3 Boolean operators. With these 3 Boolean operators, you can construct any other operators, any other Boolean operators. And here's a kind of nice little tidbit. The true and false are actually integers in Python. So false is 0. And true is 1. So that's just like a nice little tidbit. Can actually be useful sometimes. And we'll see that maybe in one of the later lectures. All right, next section, control flow. Right, what are the 3 control flow statements, and what is the difference between these 2 following examples? I will give you another 3 minutes for that. Zip. And that is that. That's a wrap for this section. The three control flow statements are if, else, and the compound of the two, which is elif, which is just a short way of writing else if. So what is the difference between these two pieces of code? Well, let's look at them and see what they print. Well, this one prints B is bigger, which is this one. And this one prints B is bigger and B is even. Okay, so what is going on here? Well, in this instance, we have a first check, which checks if A is larger than B. And these checks are the same between the two examples. The only thing that's different is here we have a series of consecutive elif statements. Here we just have if statements. And so here we first check if A is larger than B. It is not. B is 6. If B is larger than A, print else if B is larger than A, print B is bigger. And so at this point, since this condition is fulfilled, and this would be another else statement, the code this is not even being evaluated. So I could put in some code in here that's not even valid. 0 divided by 0, which should give you 0 divided by 0. Typically gives you a division by 0 error, right? But since this code is not even being evaluated because it's not reached, because, well, this elif statement catches us and terminates this whole chain here, where this doesn't trigger an error. Whereas here, we just have a bunch of consecutive if statements. Every one of these if statements is evaluated. And so all the if statements that come out true are evaluated, right? So this is true, so this print statement is being evaluated. This is true, so this print statement is also being evaluated. So if I typed in 0 divided by 0 here, this would throw me a 0 division error. This is also a good exercise. I don't think we've spent much time reading error messages in this course yet. A good point to think about how to read an error message. Well, this one is relatively obvious because it tells us, well, the 0 division error, we're dividing by 0, and we're not supposed to do that. But it also tells us in which line and what the code is there. So if you have an error like this, and sometimes this error will kind of propagate through multiple modules you've called, it's usually good to read this traceback and see where in your code the error is. And maybe that gives you a handle on what's going on. Here it's relatively obvious. We can't divide by 0. Okay, cool. Lists, and then I think after lists we just have dictionaries, and that's gonna be it for the review part of this session. So I'm gonna give you 5 minutes for this one because this one is a bit more involved. Question is, what are lists? How are lists indexed? Given this list, how would you access X? And given this list, how would you access X? And when indexing, what do the 3 values you can use mean? X colon Y colon Z. What's X, what's Y, what's Z, right? Given this code, what is the output and its type? The following code outputs FUD. What does each bracket do to the list? So here we have kind of some chain indexing. What makes tuples different from lists? And we have a trick question here. What is this output and why? And what do you think the following code does? just having a guess. All right, 5 minutes. All right, you got 2 minutes left. All right, that's been 5 minutes. Let's check out the answers. What are lists? Lists are, well, a collection of items that you can access by position. Lists can take any kind of objects in them, so they're not fixed. They don't have to all be the same type. How are lists indexed? We use square brackets for indexing lists. So it's probably not good to write that in there. Yeah, we use square brackets. I'll show that later. Given this list, how can we access X? Let's see. Well, we want to get index 1. And that way we get X. In Python, most objects are, or pretty much all objects are 0 indexed. So the first item, the 0th item has index 0. So the X has index 1 in this case. Given this list, how would we access X? Yeah, I have to, again, copy this like this. Otherwise, it's going to complain. So first we're going to take, not the zero, this is a list of lists, or a 2-dimensional list, if you will. So we're not going to take the 0th list, we're going to take the first one, and then of the first one, we're going to take the first item. So we do this chained indexing, and again, we get the X. Cool. When indexing, what do the 3 values you can use mean? So X colon Y colon Z. So that's X is the start, Y is the stop, and Z is the step. So from start to stop, give me every step element. Given this code, what is the output and its type? Well, let's try it out. And Control C. Good Lord. There we go. This is going to give us a list. And yeah, this is because here we're doing what we call slicing. So we're slicing the list and we're taking B and C. The following code outputs F, E, D. What does each bracket do to the list? All right. Let's see what this does. So this is going to take every element until the second one. So it's going to give us the, why doesn't 1 to 3 give D as well? 1 to 3 give D as well, because the stop is never included. When we're saying stop, the stop element is not included. So it's going from element 1 to index 3, but it's only going to give us 1 and 2. 3 is not included. So in this case, we're going to take from the start, because we didn't give it a start, so from the 0th element until the second one. This is the second element. So basically, we're going to take these 2, right? And we can verify that by just commenting out the rest. Right? So we got the first 2. And then we're going to reverse those 2. So, right, this is again a list of lists. So we're going to reverse this -1 from start to stop. Given a step of -1 reverses a list. And so this is just going to swap those 2. And then what we're going to do is we're going to take the 0th item, which in this case is a DEF. So I'm going to take the 0th item. And now we're going to again reverse it. And we get FED. Cool. To use the end, yeah, okay. Exactly. If we, in the previous example, because somebody asked again why this doesn't give us D as well. If we'd wanted D as well, we'd have had to leave out the 3 here. We would have just said 1 colon, and then it would have given us everything from element 1, which is B, to the end, including the end. Okay, so we've resolved this. What makes tuples different from lists? Tuples are immutable. Lists we can change. We can add to lists. We can remove items from lists. We can't do that with tuples. We can tuple support the plus or concatenation operation, but that creates a new tuple. It doesn't actually add them together. Trick question, what is this output? Why does this happen? So this is a thing that's maybe a little bit unintuitive, but it will output 3 lists, a list of lists, and each of the sublists is going to be 000. And why does this happen? Because what we're doing here is basically we have a list of lists that we multiply 3 times. So we concatenate to itself 3 times, basically. Or 3 times, basically. And then what we do is we go into that list of lists, right? And which we take the 0th element, which is the first list. And then we take the first element in the 0th list, which before we do this should be an X. And then we change that into an O. Now, why does this change the O, this into an O for all 3 of these? Well, that's because all 3 of these lists are the same object. We created one list of lists, concatenated it to itself 3 times. So now that we changed something in one of the copies, all the copies point to the same point in memory. And so by modifying one of the copies, we modify all of the copies. So this is something to be aware of in your code. Mutable objects are useful, but this is always a danger. That you can modify things that you actually didn't want to modify. And last but not least, what do you think this code does? Yeah, what do you folks think the code does? For anyone that didn't actually just try it out. What do you think? Well, here we have a more advanced version of it. Let's copy and paste that in there. Anybody got a guess what this code does? A equals square brackets X for X and range 10. Put the ranges into a list because range is a lazy object. Yeah. X will go through 1 to 10. A list from 0 to 9. Yeah, that's actually correct. It's going to be a list from 0 to 9. So this is what we call a list comprehension. Now, there's a couple things in here. Well, first we have the square brackets that cover this entire list comprehension. And then here, you might recognize what this is, for X and range. That's a for loop. So this is a way to write for loops a little bit more quickly. And if you have to collect the output from that for loop into a list. Now, do I recommend you write all your for loops as list comprehensions? No. But oftentimes, this is faster than writing the same thing writing the same thing as a for loop. And it's less code that people have to read, and then oftentimes that means it's easier for them to read. So for example, in this example, to write this as a for loop, we would have to say A is equal to an empty list, and then for I in range 10, zip, forgot a colon, A dot append I, right? So we've had to basically put in that extra step of, well, we have to append I to A. There's another difference between these two examples, actually. Who has a guess what else is, other than we had to write more code in this example versus this example? What other thing do you think might be different between this example and this example? Just a guess. Memory usage? Yeah, actually, yeah. I don't know about memory usage. Yeah, probably the for loop is a little bit less efficient. But there is an actual time, yes. Other than time and memory, there is an actual like Python objects difference between these two. The I variable, that is exactly right. It's the I variable. We can still, the list will be offset by 1. No, it won't. You see these lists are the same, right? This is a list from 0 to 9, and this is a list from 0 to 9. No, someone already pointed it out. It's the I variable. The I variable is different. And it's not different because it's named I, but it's different because we can still access I. I is 9, because in the for loop, right, what this just does is it sets the variable I to some value. Whereas X from this, let's make another field here. X from this for loop, the name X is not defined. You say, what? It's not defined, but we had a for loop with X here. So in list comprehensions, this is considered a local variable. So as soon as this is evaluated, this X variable goes away. So that's a minor detail, but can be relevant. All right. And this kind of stuff becomes also a little bit more useful when you have maybe like a slightly nested loop. You don't have to do use temporary variables. In the previous example, is there a way to unlink repeated elements? Not quite sure what that means. Oh, that one. Yes. Okay. Gotcha. Yeah, Mark is exactly right. When we were looking at this example, yeah, we could actually rewrite this. Yeah, we could rewrite this code with a list comprehension, actually, so that this doesn't work. And the way we would do that is actually a really good question. So we'll just use the copy function here, I in range 3. Doop. Sorry, my bad. I have to, yeah. Okay, so yeah, exactly, that was it, removing a set of brackets. Yeah, so so using the copy function here and using a list comprehension here, basically what we're doing is for every I in range 3, which is just, we're repeating the loop 3 times, we're generating a list, and then we're using the copy function, which basically says, give us back kind of the value of whatever is on the left side of this, whatever the object is that we're calling copy on, as opposed to point us to the place in memory, right? If we left out the copy here, oh, even if we leave out the copy here, it still works. Interesting. Oh yeah, because each of these gets evaluated. Each of these gets evaluated when we run through the for loop. That makes sense. Yeah. So this would be a way to do the same thing that we had earlier with just multiply by 3. without having this issue. Would that work without copy? Yes, exactly. That's what I just tried. Perfect. Yes. Cool. And so here you can see you can also do nested list comprehensions. I don't recommend nesting these like crazy. At some point, it's just easier to write a for loop. But write what you're comfortable with. If this is what you're comfortable with, write it this way. And again, we have basically a list of lists because we're creating a list from 0 to 10, 0 to 9 and here, and then we're doing that 3 times here. And writing out that same thing would be a bit of a mouthful as a for loop. And in general, when for loops become a bit too involved, you may have realized this when you were trying to do the homework, it can get a bit hard to read after certain levels of nesting. Okay, on to the next section. Dictionaries. I think that is, oh no, we have for loops as well. Meow. Yeah, let's give ourselves maybe 3 minutes for dictionaries. Because I want to get to the fun stuff. So 3 minutes for this section. What are dictionaries? What does this return? What does this return? What does this return? What happens when a key is looked up that does not exist in the dictionary? What happens when a value is assigned to an existing key? And what is the difference between these two code snippets? All right. All right, that was about 3 minutes. What are dictionaries? Dictionaries let us store key value pairs and let us look up the keys and change the values. What does this return? This should return A, a keys object that points to A. This should return a 1, a values object that points to 1. This should give us a tuple A, comma 1. What happens when a key is looked up that does not exist in the dictionary? Well, this is a trick question. Depends. When we're assigning to that key, if it doesn't exist in the dictionary, it's fine. It just looks up the key, and if it finds that that point in memory is empty, and we are assigning to it, it's okay with that. But if we're trying to use the value from a key that we haven't assigned a value to yet, we will get a key error. What happens when a value is assigned to an existing key? The existing value is overwritten. What is the difference between the following code snippets? The difference is you should never do this. I can't think of a scenario where I want to do this rather than this. This is just faster. The keys object is meant for when you want to look at all keys at the same time. This is meant for for loops. Natively, when you're writing a for loop over a dictionary, you're going to loop over the keys. And this is what's called, this is a dictionary comprehension. So much like the list comprehension, as you can see, instead of just giving it one value, we have to give it, well, a key colon a value. Otherwise, it doesn't work, right? In dictionary, we can't just put in values and no keys. That doesn't work. But yeah, this works the way you'd expect it to. What values will A and B hold in the following code? A will be the keys and B will be the values, right? And so we're gonna iterate over key value pairs one at a time. So the first is gonna be the first key and the first value and so on and so on. Here's another nifty trick involving enumerate. Oftentimes you want to keep track of where you are in a for loop. For that, we have a function that's called enumerate that lets us basically, that returns a tuple of, well, the index in the loop and the variable from, the value returned by an iterable like this, for example. So here you can see we're just printing the index and the value, and this is very useful. So this way, you don't have to do, you don't have to write some kind of storage variable and increment it every time you iterate over here. Enumerate solves that more quickly. Here's a thing that I found in these notes from Mark when I was going over them that I actually didn't know you could do. So this is really nifty. So here we have, again, the same dictionary. We have this nifty dictionary comprehension. This just gives us where in this dictionary, the keys and the values are the same, except the keys are characters and the values are ints. But the nifty thing is when we use enumerate over this char map.items, which again gives us the keys and the values, we can do sequence unpacking here. And I knew you could do sequence unpacking, but what I didn't realize was you can even unpack this tuple, right? So items gives us a tuple of keys and values, and then enumerate wraps that in another tuple. So now we have basically, now the way it looks is enumerate gives us back a tuple that is the index, and then another tuple with the key and the value. And if you specify the structure, you can actually natively in the for loop unpack these. And this also works for when you're doing regular assignment, right? So 1, comma, 1, comma, 2, 3, you could say is A, comma, B, comma, C, right? This is the same concept as this. And this lets us print, again, iterate relatively quickly through through this dictionary, and also lets us keep track of maybe how many keys we've been looking at. And again, if you wanted to write the same thing, without enumerate, you would have to use something like this. And this works too, but it's more code and it's more things to keep track of. And so it's just not recommended. There may sometimes be reasons why you may not want to count certain loops or something like that. Then you can't use enumerate, and then you want to manually keep track of this index. But really, most of the time, enumerate is going to do the job for you. I think we're going to skip for loops. This is just a lot more on how to slice, because I've prepared some really fun stuff, and I would be really sad if we wouldn't get to go over that today. So let's skip this for loops section for now. This is maybe something to do at home. And there are, I think also, yeah, here are the solutions for how you can do that. Same thing. All right. It is time for what you've been learning, to put what you've been learning into practice to solve a children's math puzzle. So this is something I actually tried out when I was first learning Python back in college, and didn't know what I was doing at all. So below is a math puzzle for third graders from a town in the highlands in Vietnam that went viral through an article in The Guardian. And it's a number snake. So basically for each of these boxes here that are blank, we have to put in numbers from 1 to 9 so that this equation holds. And first, let me put in, somehow this got reformatted. All right, there we go. Okay, this is really weird. Anyways, first let's put this in a more readable form where we use different letters, because this is not very easy to look at. We're just gonna write the same equation out, but we're gonna use letters for each of the different missing numbers. And immediately if we look at this equation, you might think, well, this is impossible to solve. You have one equation and you have one constraint, and you have like, I think it's 8 unknowns or something like that. You can't solve it. The original question, however, doesn't ask for the solution. It just asks for a solution. And which is because the equation has many possible solutions, and we'll take a look at that later. And so if you look at the equation this way, you can simply clean that up a little bit more, and then it's actually not too hard to guess combinations that solve this equation. But why would we do that when we can have the computer do it all for us? And so the task here is we want to find all possible solutions to this equation. Spoiler alert, there's 136 different solutions, and many of them are very similar to each other, which is why it's relatively doable to guess solutions. And so let's think about this real quick. So we have our equation, and we want to find all possible solutions. Well, we can just try, we should first look, is it feasible to try all possible mappings? So basically all possible mappings are different combinations of putting in the numbers 1 to 9. Can we try that out? And this is actually what's called permutations. So what's the big O for trying out all possible permutations? That's what we should figure out first. Then let's figure out how we can generate all possible permutations of these values 1 to 9. We will Google this. Hell no, there's no way I'm gonna write that myself. And then we're going to loop over all the possible mappings of the values 1 to 9 for 9 to the power of 9. Actually, Mark says the big O is 9 to the power of 9. I don't think so. We will also Google this. And We will loop over all possible mappings of the values 1 to 9 for the letters A to I in this equation. And then we'll only store the valid mappings in a list of tuples. That seem understandable? So this is in general what we want to, yeah, exactly. That's right. Emily explaining why that the constraint is we can only use the numbers 1 to 9 once each. It's like a Sudoku, but kind of the linear Sudoku. All right, let's start at the start. Is it feasible to try all possible mappings? And what's the big O for trying out all possible permutations? Well, let's Google big O notation of permutation. Oh, would you look at that? Someone else has thought of that before. Let's read this question. What would be the big O notation of the length of the list of permutations of the characters of a list of word of length? Okay, this is maybe more than we need. Their problem is more complex than ours, but it turns out they give us an answer right here. It would be like n factorial for each word, where n is the characters of that word. But O of n factorial is the complexity of a single word, not a list of n words. Okay, but we have a single word. We have a list, we have 9 numbers. That's the same as having a single word. So for us, it's O of n factorial. So let's get back into our code. We will just import the factorial function from math. And let's see what the factorial of 9 is. That looks really manageable. But just to show you why I checked this, if we check the factorial of 20, this is too much. We can't run this many loops. We will never stop. And this course is already taking too long. But factorial of 9 is doing fine. We'll create our own factorial function on Thursday. That is very exciting. You folks are in for a treat. But for now, we are going to say check. We can definitely try all possible mappings. There's only like 400,000 of those. That's fine. We have to generate all possible permutations. Because we're a bit short on time, I'm not going to Google this. But basically, in the itertools module, there's a function called permutations for exactly this purpose. We don't have to write it ourselves. So the itertools permutations function, we can just give any iterable, and then it'll give us all possible permutations of that iterable. And so in our case, we're just going to give it the values from 1 to 9, right? And we're going to say, okay, our solutions, we're going to store this in float underscore solutions. And then we're going to say, well, for our variables in these permutations, all possible permutations, if this equation holds, right, and you can verify that later if you want, this is the same equation I wrote upstairs, we're going to append this set of solutions, tuple of this set of this particular permutation to our float solutions. And then let's try that out. And it turns out there are a lot of these solutions look very similar. Here, what I've done is I've written a print statement that tells us how many solutions there are. This is another, you might be a bit confused what this is. This is another way of formatting strings. As I've alluded to in a previous lecture, we could give an entire lecture series on just formatting strings. This is the way I like to do it. This is what's called an F string. It's new in Python 3.6. It works very similar to the dot format method that we tried in a previous lecture, except I just write the code that I want evaluated in curly braces directly. And so basically everything that's not in these curly braces in this string is just treated as regular string. And then this thing is in curly braces, so it'll just run this code, and whatever comes out of this code, it will turn into a string. And so I'm going to use the len function on our float solutions, and we have 128 solutions. That's awkward. I told you earlier that there's 136 solutions. So this gives me an opportunity to talk about another obscure part of the standard library, which is the decimal module. So potentially this has something to do with that we're using floats, and we're going to get into that a little bit later about what that has to do with using floats. And the more experienced folks from other languages probably know where this is leading, but please don't spoil the surprise. So what we're going to do is we're going to use, instead of floats, we're going to use decimals. Decimals are a bit more precise than floats, or a lot more precise than floats. And so what we're going to do is the only thing that's different from the previous time is we're going to replace all of our numbers that we had as integers previously. We're going to turn those into decimals. And now you're going to say, well, integers, floats, why are you calling these floats? We have divisions here, and so these divisions are going to return floats. And as soon as one of these elements turns into a float, this whole thing is going to be a float. And so that's why I'm saying this is going to be our float solutions, and here we're going to use decimals instead of all of our integers. And so all the things we're going to get are all going to be decimals. And then here we again loop over our permutations, and then again we check our huge equation. And the only thing that's different is we've turned all the constant numbers into decimals again. And here I'm doing a thing, I'm converting them back into integers. This is just because the integers print more nicely than decimals. We wouldn't actually have to do this. And so now, when we do this runs for a second. Yay, we get 136 solutions. So what's going on here? Why do we get more solutions when we're using decimals? And we want to know, to answer these questions, we want to know which of these solutions are unique to decimals. Before we answer that, we also want to ask, are all of our float solutions included in our decimal solutions, right? So here I made a different list called decimal solutions, in which we're collecting the solutions that are that we got using decimals. This is a perfect use case for using sets. And you might say, well, this is a children's math problem. Why should I care? This type of operation you will actually have to do somewhat frequently when you work with data frames, because you will have different data formats, and this group and this collaborator is going to format the data differently that way. And all of a sudden, you have to check if the column names are all the same. And you can use that, for example, you can do that using sets, for example. And you have to check, oh, are all the columns in this one included in this one or not? All this kind of stuff is useful to know how to check. And so we're going to use sets here. Sets can only contain one of each item. So they're basically like half a dictionary, like only dictionary keys and no values. And they only take hashable, meaning immutable objects. You don't have to know the difference here. Think about them as immutable objects. We only want to put immutable objects into sets. And to accommodate the sets, one thing we did earlier was instead, we made a list of tuples instead of a list of lists, because lists are mutable. So if we'd made a list of lists, the sets would have complained that lists are not a hashable type. And so we can't make a set of lists. We can make a set of tuples though. And that's what we're gonna do here. And we converted all the decimals to ints when storing them as solutions. I found out later that I actually didn't have to do this. But I tweeted about this yesterday. So if you want to stalk me on Twitter, you can figure out why you don't have to do this. And basically what we use sets for is comparing, well, in this, comparing different collections of unique items and seeing if they have items in common, what items are different between two sets, these kinds of operations, right? And so in our case, we're going to use the set.difference function to find non-overlapping parts of the sets. And so we're just going to import ppprint. We're going to make 2 sets here. We're going to make one decimal solution set and one float solution set from our decimal solutions and our float solutions, right? We're just using the set function here to generate a set. And then to get the decimal only solutions, we say decimal solution set dot difference float solution set. And that's going to give us all solutions that are part of the decimal solution set that are not contained in the float solution set. And here I'm using an F string again. And in this F string, I'm also asking if all the float solutions are included in the decimal solutions. For that, we can use the isSubset function. So we can ask if the float solution set is a subset of the decimal solution set. And then I have another F string here where I'm printing out how many solutions are in our decimal only solution set. And then finally, we're gonna print out these decimal only solutions. And these don't look like anything special. So there's 8. First of all, we know, okay, all of the float solutions are included in the decimal solutions. And second of all, there are 8 solutions that we only found using decimals. And these don't really look like anything special. So let's go through one of these by hand to see that we're not crazy and that these are actually true solutions. So computers are great and all, but sometimes you gotta get your hands dirty with some numbers. And so we're just gonna take this equation and just plug in the numbers. And you can verify this by hand on your own if you wanna do later. But if you trust that I can do simple arithmetic, which you probably shouldn't trust, this one comes out correct. So the equation holds for one of these solutions at least. So that is a good indicator that probably many of these solutions or all of them are actually correct. So something was wrong when we were using floats. And so what we're going to do is we're going to print out what the left side of this equation looks like for all of these decimal only solutions if we're using the original notation, right, where we weren't using decimals. So let's look at that. And lo and behold, we now know why none of these were caught when we were using floats, because they don't evaluate to 66. They evaluate to 65.999999999. Okay, that's awkward. How do you build around that? And why is this going on? This seems like it's basically 66, but it's not. And so this has to do with how floats work. And this is an artifact of what we call float imprecision. So floats are stored in memory as fractions, where some of the bytes represent the numerator, so what's on top of the fraction, and the denominator as a power of 2 is also means that the larger your float is, the less precise it is. But also this means you can't represent every possible float this way, right? Because we know there's an infinite amount of numbers. I forget what those numbers are called. I want to say real numbers. Yeah, real numbers. There's an infinite amount of real numbers, right? So that means we can't represent an infinite amount of real numbers, even if we chose an upper and a lower bound, because there's an infinite amount of them, right? And here you can see how that works out in practice. This is a hypothetical 8-bit float. Python uses 64-bit float. But these are the numbers an 8-bit float could represent. So all the black lines are different numbers they could represent. And so what you can see here clearly is there's a lot of numbers close to 0 this can represent. As we go further away, less and less of these numbers are represented, right? And so basically this accounts for this error, is that Python can't represent all of these numbers correctly. as floats, and that's why some of these solutions weren't caught, because the imprecision caught up with us. And so here are some idiosyncrasies that have to do with floats. So for example, if you take 0.1 plus 0.1 plus 0.1 and ask if that's the same as 0.3, you'll get a false, which is because these are not exactly 0.1 and this is not exactly 0.3. And so the two sides of this equation are not equal. And the classic example is you add 0.1 plus 0.2 and what you get out is 0.3. So does this mean we should be using decimal types instead of floats in our computation? Absolutely not. This was just to show you that if you get a bizarre floating point result, right, or like one of these, so that you know why that is. And sometimes this can have effects that are actually important. This should also tell you that if you are doing, for example, some kind of computation that has to be very precise in floats, you want your floats to be as close to 0 as possible, because there the density of numbers that floats can represent is much higher than you go further away from floats. And so that's the lecture, the lesson here. And now I'm very sad that we're already at 2:30, because I have, this would be so fun. I have another huge example set here. I don't know if we're gonna roll that into the next lecture, or if we're gonna ask you folks to do this at home. But I have a whole section on working with city bike data here that some of the code was from Mark, and then I added, I think, a good chunk to that. So that would probably take us another like 20 minutes or so to go over.
Yeah, let's save that for another time. And there is also a lecture, I think, at the end that we haven't scheduled, I think. So maybe if there are things like this that are left over, we can put that in there.
Yeah. Yeah, that sounds reasonable. Again, if you can't wait to get your hands, working on some more code, I recommend just working over this section on your own. I hope I've made it understandable enough that you don't need me narrating everything. But if you do have questions about this, pop into the Stack Overflow and just tag me on your question, and I'll be more than happy to help you with any of these things. I just like this section a lot because it's actual like real data analysis with real data from New York City. And we got some interesting results in there too. So, but to get those, I guess you have to do it on your own. All right.